Welcome back. Let us now take what we know about the components of a data path and make it more efficient using the concept of pipelining. We begin with the data path that we looked at previously. The blue components are the structures that hold state and which are updated at the end of every clock cycle. This data path is capable of executing one instruction every clock cycle, but the clock cycle is determined by the longest combinatorial path through the data path. The longest path most likely occurs at the store instruction as illustrated by the red lines here. This limits the performance. Pipelining is a technique where we execute instructions like on an assembly line. It involves separating the steps of execution with registers. These registers contain everything that is needed, including data and control signals. The phases, or stages as they are often called, are named after the main function done in that phase. This means that before we have finished with one instruction, we begin the execution of the next and overlap their executions. This is a form of instruction level parallelism, or ILP. The main advantage is that the clock cycle can now be reduced and is determined by the maximum combinatorial time of any stage. Most likely this is the time of reading the data memory. The best analogy to pipelined execution is to think of factory assembly lines pioneered by Henry Ford, but the origins of the word comes from the ability to transport oil and petroleum of different qualities in the same pipeline, one after the other. Here we illustrate the capability of a 5-stage pipelined processor to overlap execution of instructions. Let us use the short name of the stages: IF, ID, EX, MEM, and WB. Consider a sequence of clock cycles. In the first cycle, instruction 1 is fetched. In the next cycle, the first instruction advances to the ID stage. At the same time, instruction 2 is fetched from memory. Thanks to that there is a separation in form of the instruction register between IF and ID, they are kept separate. In cycle 2 and 3, the instructions advances in the pipeline, and in the 5th cycle, the pipeline is full, with one instruction in each stage. After this, the clock cycle, there is a possibility to retire one instruction every clock cycle. This is another and simplified view of pipeline execution, but it shows exactly the same thing as the table on the previous slide. Life is not always so good that you can retire one instruction every clock cycle in a 5-stage pipeline. There are hazards that complicate things. The first one we will introduce is the structural hazard, which occurs when a hardware component needs to be used by two instructions at the same time. Here, for example, when the first add instruction would like to store the result in register X1 in the same clock cycle as the sub-instruction would like to read the same register, how do we deal with that? We generally resolve such situations by stalling the newer instructions affected by the hazard and letting the older ones, which had proceeded longer in the pipeline, progress. Stalling is achieved by freezing the pipeline registers immediately preceding the newest stage that experienced a structural hazard. In this case, the sub-instruction will freeze in the ID stage, which also means that the following instruction is frozen in the IF stage. As you can see, this leaves a hole, a bubble in the pipeline. This is achieved by clearing all control signals in the pipeline register between the ID and EXE stages so that it effectively becomes a no-op instruction in the pipeline. To sum up structural hazards, this can happen when two instructions or more need the same hardware resource simultaneously. Besides stalling the newer instructions, you can also resolve the structural hazard by adding more hardware. The simple 5-stage pipeline that we are working with here has no structural hazard by design. The issue shown on the previous slide has been resolved by realizing that the register can be written in the first half of a clock cycle and read in the second half, so even if the read is from the same register written, there is no structural hazard. The next kind of hazard is worse and caused by data dependencies. In this example, the add I instruction needs the value in register X1, which is produced in the previous add instruction. As you can see from the pipeline diagram, it is needed already in clock cycle T2, while the value is not written back to the register by the add instruction until clock cycle T4. You can resolve this by stalling the newer instructions for 2 clock cycles, but that wastes a lot of performance. The common technique used to resolve this is to use something called bypassing or forwarding. This is done by observing that the value you need for the add I instruction, in this case, already exists on the output of the IALU in the pipeline. If we can find a way to forward this value to the ID stage, instead of taking the register value read, we have resolved the issue. Here we have added the necessary hardware to include forwarding. The main structures are the 2 big muxes after the output of the register file. From here you can select if the data should come from 1. Register file, 2. Output from the X stage, 3. Output from the memory stage, or 4. The PC from jump and link instructions, which I will not explain more now. These muxes are controlled by 2 control signals, A source and B source, which are very similar. You can make a logic expression that checks the source and destination operands of the instructions in the ID, EXE, and MEM stages and sets the control signals accordingly. The figure also has the stall signals mentioned before. It freezes the PC and the IR from being updated and inserts a bubble, no up, to the exit stage. Is there still need for such a signal? Unfortunately, yes. If the 2 instructions are data dependent are a load instruction followed by an instruction using the value loaded from memory, we need to stall 1 clock cycle. The logic for that is shown here. Compilers are usually good at finding these cases and will separate the load from a using instruction by putting some other instruction there. In fact, the very early MIPS processors did not have interlocking, which is the name for the ability to stall on data dependency. It did not have that in hardware and relied on developers or compilers to insert a no operation after the load, achieving the same result. The third kind of hazard we can experience in a pipeline processor are control hazards. For these instructions we need 1. Maybe evaluate a condition, and 2. Possibly calculate a new PC. Jump instructions need the branches PC and offset to calculate the new PC. The jump register needs the register value instead of the PC. Conditional branches need registers for the condition and then PC and offset, just like the jump. Regular instructions need simply the PC to figure out the next PC, adding by 4. In all cases, the opcode is needed to decide which one it is. Let's begin with optimizing the common case, sequential code. This means that unless anything else is stated, PC is loaded with PC plus 4. If we have a jump, as in this example, then we know that in the ID stage we have already read instructions I3 at address 104 wrongly, as jumps are unconditional. We therefore need to kill this instruction, not stall, remove it completely. How do we do that? The solution is quite similar to stall, but here we replace an instruction with a bubble, no up, instead of simply delaying some instructions. First, we need to insert a mux after the instruction memory, which in case of a jump being decoded in the ID stage will kill the current instruction in the IF stage. The logic is quite simple, as you see here. In this example, let's assume that I1 is in the X stage and I2 in the ID stage, and we detect a jump. We have already read the wrong instruction in the IF stage. Our source D signal is sent to kill, bubble. Then, when going forward, PC is set to 304, which is where the next instruction will be read. The bubble enters the ID stage, and I1 and I2 continues down the pipeline. Do we need to consider an interaction between stall and kill if conditions hold for both? Yes. kill will always take precedence over stall. If both conditions are true at the same time, you'll have to do a kill. Here are two other ways of illustrating this for jumps. Let's consider a sequence of clock cycles. In the first clock cycle we fetch the add instruction, second clock cycle we fetch the jump instruction, third clock cycle we fetch the add immediately following the jump, but we notice now in the ID stage of the jump that we did it wrongly, so for the next clock cycle we kill the add instruction, denoted by the red dash, and we instead fetch the branch target, and so on. We can illustrate this in a slightly different way by focusing on the resources, the stages, rather than the instructions. So it shows the same thing with the clock cycles here, and in the third clock cycle we have the bubble that follows the pipeline. Consider now conditional branches. In fact, all branches are from the hardware perspective conditional. It's just that for unconditional branches we use register x0 in the comparison, which are always 0, so a BEQ x0 x0 will always be true. The example shows an add instruction followed by a branch. The target is at address 304. The branch condition is not known until the exit stage, compared to the jump when we knew about it in the ID stage. What should we do in the ID stage in this case? In this case, if the branch is taken, which we know in the exit stage, then the two instructions already in the ID and IF stages also need to be killed. It's not sufficient to stall the instruction in the ID. We need to add also a kill signal for the ID stage. It's basically the same as a stall, except that we don't stop the pipeline as we do when stalling. And here we also see the logic needed to calculate the branch target address. Here are the other views of execution of branches. Clock cycle 1, the add instruction, clock cycle 2, the branch, clock cycle 3, we fetch the add instruction, and clock cycle 4 we fetch the second after the branch. And not until then we know that the branch is going to be taken. And therefore we have two bubbles between the branch and the branch target. And here's the same view for the resource usage view. So as you can see, jumps and branches are detrimental for the performance of programs. Later in the course, we will investigate methods of improving the performance using branch prediction, which is a way to improve on our simple prediction here that we always fetch the next instruction in sequence.